Your packet, if you guys can turn to page 43. The handout that I gave you is the homework for tomorrow. I forgot to put the AP practice for Unit 6 in your packet, so that's what you guys just picked up. Okay, now U substitution. This is basically the reverse of derivative chain rule. It's a little bit harder to put things back together than with chain rule. Chain rule, you're just identifying the inner portions and you're just kind of finding the derivatives and just putting them together, or just laying them all out. But putting things back into its form from where it came from, a little bit more challenging. So we have this U substitution method to kind of help keep track of what we need to put things back into the proper function form. So example 1, let's say, let's do some review here. Let's say f of x is sine of 3x. We know we got to go through a little bit of chain rule. L size derivative times n size derivative. So sine of u becomes cosine of u times u prime, right? So whenever we, that's why I like to have us memorize the rules in terms of u and u primes, because we're always understanding that there is the chance that there, sorry, sine of u, that there's a chance of that u prime where we got to go through chain rule. Okay. So we know sine of 3x is just cosine of 3x times 3. Okay. But what that means is if I were to find the antiderivative of 3 cosine 3x, that must bring me back to what? Sine of 3x, right? Because if this is my derivative, then I should be able to make my way back. But it makes it a little bit harder, because if I know that integral of 3 cosine 3x dx, I know that cosine becomes sine 3x, but how do I know that I need a 3 there and that this will disappear? It's a little bit harder to kind of see that kind of going backwards and just knowing, wait, how do I know that I need a 3 there? What do I do with that 3? What if the 3 wasn't there? Then it's going to be a little bit different. So U substitution allows us to have a different variable to kind of keep track of what needs to be in place when we do the antiderivative. Now I have all these steps identified. I think it's easiest if we just kind of went through the example and I kind of walk through the steps as we use them. So let's look at example 2 here. Integral of x times x squared plus 1 to the 15th. If we did not, if we didn't have this U substitution, what we're going to talk about, and if we're trying to force it into a power rule problem, what's the challenge of this problem? Okay. Boiling out this 15 times is really, that's kind of a pain. We are, we can go through something like Pascal's triangle, but that's not something we got to worry about. So, but we always want to explore power rule first. Can we expand? Can we rely on just power rule to get to our answer? And that's why it's important that I skipped a problem like this from yesterday. But the idea is that even though a problem looks complicated, we always want to explore power rule first. This one we can do power rule because we just have to expand and then clean up the denominator and then do power rule, right? So I know that our tendency after today, we're going to think of U substitution as our first step, but I just want to keep reminding us that power rule should be our first option. If we can't do power rule, if something feels out of range of power rule, then we can explore U substitution. But this is within range of power rule, and even though this looks complicated, if there's only one term in the denominator, we can clean up and just do power rule. Okay. But we explore power rule and we say this is too difficult to manage. So we're going to go through U substitution. So U substitution is identifying a portion of the problem and then simplifying the problem for us. So this is not always going to be the case, but I think this is a good first step for us to identify is look for your parentheses. Right. Whatever is inside your parentheses, chances are that's going to be your U value. Right. So if I can create a set of parentheses, then that's going to be my U value. Now we're going to see exceptions all over the place, but that's kind of like a first good place to start. So what could be our U value here?
X squared plus 1.
X squared plus 1. Okay. And we always want our U value to be something that is more than just X. Okay. If you let your U value just be X, you're not going to create a simpler problem. The whole idea is that we want to create a simpler problem. We want to see, do we have everything lined up? And if there's any leftovers, that we keep track of those leftovers. Okay. So I want us to underline the X squared plus 1, and I want you to underline the dx, right? Because this is going to be our priority. Our priority is to replace these in terms of U, see if we can find a rule that we can match, and we're hoping that this X will go away. All right, so we'll say U is equal to X squared plus 1. And slowly but surely, we're hoping that everything will just turn itself into U, and then we can identify a rule that applies and then apply the rule accordingly. So the next step is we want to find a derivative. We want to find the derivative of U with respect to X. So we're going to say du over dx is equal to. Okay. So we're just going to find the derivative as we see it. X squared becomes 1 becomes 0. Okay, I'm going to cross multiply here, but my goal is I already have a replacement for X squared plus 1. I want to find a replacement for dx. So I can cross multiply here and say 2x dx equals du. Dx equals du over 2x. Okay. Now we're just going to replace what we underlined. Okay. Everything else don't change. So the x is going to stay for now. X squared plus 1 turns into u. The 15 stays. And dx becomes du over 2x. Now, if I cannot get the x's to go away, that's an issue. Okay, we cannot move forward in the problem unless we can resolve all the x's. Okay, we cannot split up a problem and say, okay, power rule here, plus c, and end the problem. Okay, if the x's do not cancel out, we have to revisit the problem and see what we can do to get that cleaned up. But in this case, will the x's cancel out? Yeah. Yes, that's a good sign. Okay, so we know that we're on the right track here if we can get everything in terms of u. Now this 2, we're going to put this 2 here to make it a little bit cleaner to look at. 1/2. Let's push it out here as 1/2. So 1/2 integral of u to the 15th du. Now, one thing to note is if you go through U substitution, you should be staring at an easier looking problem than what you started with. If you go through U substitution and it ends up being as if it looks the same or more complicated, then we didn't go through it correctly, right? Our U value is going to be a rather significant chunk of the problem because we want to simplify it and produce an easier problem as well as see if our variables cancel out and then check to see what leftover coefficient we got to keep track of. Now, is there a rule for this? Yes, that's power rule, right? So we just go through power rule. 1/2 is going to stay. U to the 15th becomes what? U to the
16th over 16th.
Yep. And then plus C. Okay. Now, do we start with, this is our answer, but do we start with a U variable? No, we started with the X variable. So we want to make sure we bring the X variable back into our answer. We did all the calculus in terms of U. but we're going to bring x back because x was what we started with. So I'll put the coefficients together. Okay. Much more efficient than having to FOIL all this out, do power rule, and then get it back in the factor form, right? We can jump to our answer a lot quicker going through, yeah. I just multiply the coefficients together and I push it out. You can put it in the denominator as well. I just find it cleaner to put as a coefficient. Okay, example 3. We always want to look to see, do we have a rule that we can apply directly, but that's too complicated for one rule to handle. So we can't split it up, right? We can't say, oh, this is power rule and this is some other rule. We can't do different rules across multiplication. This is all connected, but we don't have a rule that can handle that mess of a problem. So we look to U substitution. What could be our U value?
Square 2x cubed.
It's a little too much. 2x cubed, right? So for now, let's just think about parentheses, okay? Down the line, we are going to talk about, okay, sometimes you're going to see different sets of parentheses, and then you're going to have to kind of do some trial and error. But right now, your first target is your parentheses, okay? It may not always work out, but that should be the first place we look.
But like the secant squared, like the squared goes out, like it's kind of messy or something.
Right, but we do have a rule for secant squared, right? So okay, so let's find let's do our U value here. U is equal to 2x cubed. du dx. We're always going to find the derivative of u with respect to our independent variable x. What's that derivative?
6x.
Okay. We're going to try to get the x by itself. And then you're going to rewrite your problem, but you're only going to replace what you've underlined initially. Okay. Everything else, copy back into your problem. Right. We cannot move forward with U substitution unless the x's go away cleanly. Do the x's go away?
Yeah.
Yes. It's okay to have leftover coefficients, but we cannot have any leftover x's. If we do, then we either did something wrong or we gotta explore a different method. Okay. Where can I put that 6? 6. Okay. Do we have a rule for secant squared u?
Yes.
Now, if you think about your derivative rules, right? Tangent derivative of secant squared. So, and antiderivative of secant squared will bring it back to tangent. And I see some students forget to put the x back. That's a minor issue. You're still getting majority of the credit points, but then make sure you bring your u back in terms of x at the end. Okay, questions so far? All right, number 4. Our first option is always power rule. Can I expand and do power rule? But in this case, am I able to do anything with power rule or expansion? I'm stuck, right? That order of operation doesn't allow me to distribute that x cubed through that radical. I cannot. I explored it. Power rule expansion is not going to be a valid option. So we know we have to maybe go through U substitution, but let's get a parentheses to show up. So how can I get a set of parentheses to show up so we can? Yeah, inside the radical, right? So let's make it 5 minus x to the 4th. the 1/2 dx. I'm just going to replace the parts I underlined, keep everything else. Do the x's go away nicely? We're going to put that -4 in the front as -1/4. Nice and clean power rule, right? Flip that fraction up as 2/3. 2/3 times 1/4 is 2/12, which is 1/6 or -1/6. And then we bring our original variable back, right? Because we have our answer, which is are going to put it back in terms of the variable that we started with. All right, any questions so far? Now, I want you to observe something about the U value here. Everything worked out, very cleanly in terms of everything canceling out so nicely. It's not always going to be the case, but it's nice to be able to look at a problem and kind of predict what's going to happen. What do you notice about your U value that makes it so nice or are we able to predict if our x's are going to cancel out?
It's 1 above.
Good. So we look at that difference, right? If our U value has a degree that is 1 above the remaining x, things are probably going to work out pretty well because your derivative is going to produce a degree 1 less, and that should match up with what's outside. So that's nice, right? 2x cubed with x squared, that's going to be a nice pairing. X to the 4th with the U value, x cubed being the leftover, that's going to be a good pairing because the degree is going to eventually match up. So if you see those types of relationships, it's going to be an easier problem and you can kind of predict things will work out. It's not always going to be the case, and we'll talk about the problems where you don't see things working out and ways around it. Okay, so let's look at the next page. Are we okay with example 4? Okay, now this one proves to be a little bit more challenging because first off, we don't have a rule that can handle that mess of a problem, right? If it doesn't match exactly with the rule that's available to us, we don't have a rule. Oh, that's something that I want to point out as well. We cannot get creative with our integral rules. We can't say, oh, wait, this rule and this rule, I can kind of make things match and adjust it and create a new rule out of it. Okay, our integral rules are very restricted. If it doesn't match exactly like the rule that you see in front of you that's available to you, it's not a rule that you can be creative and make up. Okay. Now, so we don't have a rule that's looking like exactly. We have a rule for secant tangent, but we don't have a rule for tangent to the 5th and secant squared. But maybe we can create a set of parentheses and explore what could be our U value. But here, if we want to create a set of parentheses, we're going to see two sets of parentheses, right? How can I rewrite tangent fifth x?
Tangent x to the power.
Yeah, so right now I don't want to do too much with factoring. I just want to see, first I recognize there is no rule that can handle that mess of a rule, this mess of a problem. But my next option is U substitution, but to do U substitution, I want to see a set of parentheses. But I see two sets of parentheses. And so we have to explore our options, right? Maybe our U value is tangent, but maybe our U value is secant. But let's think about the derivative and see which one will be a better fit. If my U value is secant, what's the derivative of secant? Secant tangent, right? Secant tangent will take care of one tangent, but it's not gonna take care of the other four. What if the U value was tangent of x? The derivative would be what? Secant squared. That's a better fit, right? All that secant squared will pair up and go away for us. Okay, so it's nice to kind of look ahead, and especially if you have two potential U values, think about the derivative and see which one could be a better fit down the line. Tangent's derivative is secant squared x. Solve for dx. All right, so I underlined the parts that I'm focusing on, right? I just want to replace what I underlined and not try and do too much at once. Okay. I underlined the tangent. I can replace that with u to the fifth. Secant x squared, I'm not going to resolve that just yet. Dx becomes du over secant squared x. And all the x's go away.
Yeah.
Yes, that's a good sign. All right, we know we're on the right track. And then next question, do we have an easier looking problem? We do. And we have a rule available in front of us. Okay, so again, we can have power rule to apply. And then bring your original variable back. Example 6, we do see a set of parentheses, or two sets of parentheses. But what's always our first option? Yep, can we do this problem with power rule? Yes, there's only one term in the denominator, right? So there's no need for U substitution. If we go through U substitution, we're going to get stuck because we're not going to find something that's going to match up nicely. So, all right, there's only one term in the denominator. I can just split up into individual fractions, clean it up, treat it like two separate problems, and power rule my way through. I can force this y up to the top. I can subtract exponents here. Right. No need for U substitution, right? Power rule can handle this. Flip the 1/2 up, it'll become 2. 2 times 3 is 6. You can leave it as rational exponents or bring them back as radicals. Either way is fine. I'm just going to leave it as rational exponents. All right, example 7. First option, power rule. Can I distribute and clean this up?
No.
No. Order of operation prevents me from doing it. Okay, let's see if we can get a set of parentheses to show up. Okay, what could be our potential U value? X plus 3. Do we see a roadblock ahead of us though?
Yeah.
Yeah, the degree is not going to clean up the way that we would like, right? If it was x squared plus 3, be a much easier process. We're still going to go through our process, but when we hit that roadblock, we can discuss, maybe we can find a way to work around that, okay? All right, so U equals x plus 3. What's the derivative?
1.
1. Okay, I'm just going to focus on what's inside parentheses here. Right, just what I underlined. So just like what we suspected, there's this x left over, which is not going away. We cannot separate this process and say, oh, power rule here, and then end the problem. If the x's are not going away on its own, we got to find a way to resolve it.
Double substitute.
Yes, that is what we're going to do here. So we see that the x is not going away on its own, but maybe there is a way that we can replace this in terms of u. Right? Do we see something that we can replace x with what we've been given? We have this to play with, right? We have this relationship. So what if I rearrange this equation and made it x equals what? Minus 3. So there's my way out of the problem that's in front of me. Now, when I make the substitution, I'm still not going to be ready for power rule, but at least I can work my way towards it, right? Before I wasn't able to distribute, but now I can distribute and I can clean this up and get it ready for power rule. And so this is my workaround. This is called the change of variable method, where your original set of substitution didn't quite get the x to go away, and we looked for a clever way to get that variable to be replaced in the variable that we want. Okay, so distribute that u through. 1/2 plus 1 is 3/2. Okay, go through power rule. Okay, am I done with the problem? Oh, still bring what back?
X was the X.
Yeah, bring the x back. For some reason, at least from previous years, students would be very good about replacing the u back in terms of x, except for this problem. Students tend to more often leave this in terms of u. I guess maybe because you already went through a set of substitutions, so you feel like you've already gone to the end. But just remember, if u is in your answer, typically, if you ever go through U substitution, make sure you bring your original variable back, right? You want to end with the variable that you began your problem with. Okay, example 8.
Yeah.
I can't distribute. I do see a set of parentheses. What could be the U value? Right, now this seems strange, right? It's like how am I going to get this to cancel out with a degree that's even higher? But again, anything that's left over, we can look for a way to get that replaced with the equation that we're going to build off of that U substitution. Okay, what's the derivative?
-1.
All right, we're kind of stuck here, right? We can't move forward until this x is resolved, or x squared is resolved. So maybe I don't have a substitution for x squared, but I can find a substitution for what? X. So what's x equal to? You might, yeah, 2 minus u, 2 minus. So I move the x over to the right side, move the u over to the, sorry, x over to the left, u to the right. So x equals 2 minus u. Okay. So this is my substitution right here. It's going to require a little bit more cleanup. I've got to foil and distribute, but there's still a path towards my towards power rule, right? Just requires a little bit more algebraic work.
Also, do you move the -1?
Yeah, so I'm going to move that negative in front here. This is what I'm going to do. I'm going to rearrange it in this way. It feels a little bit cleaner this way, but. So the negative I pulled in front. I like to have my individual variable first, and then I can worry about the foiling. If I can foil this out, then I can distribute this through. Just distribute that negative through. Everything's ready for power rule. I'm going to go through power rule, clean up my coefficients, and then bring your original x variable back. Okay, next page. Okay, involving U substitution with definite integrals. Basically, it's just one step beyond this. You just plug in your upper and lower bound after you finish your problem, right? Okay, so let's look at example 1 here. Remember, if you ever see bounds in your problem, that's always the last thing that you do, right? We never involve bounds with the expression we see in front of us. We got to transform it into its antiderivative before the bounds has any effect. So I'm just going to ignore the bounds and just focus on my first priority here. Okay, can I rely on power rule?
Yeah, it's messy.
I could, right? But anything more than the degree 2, we like to explore other options, right? It's not terrible, but it's not as easy as we would like. Okay, so what could be our U value? Okay. Okay, so I got it cleaned up to be integral U cubed. I look after my U substitution, I'm staring at a much easier problem than what I started. This is a power rule problem. Take my antiderivative, bring my original variable back. Now I can involve my bounds. Upper bound first. Minus the lower bound. (16/4) minus 1/4 is 15/4. This is my area related answer. Okay, we're going to save some space, and I want to show a different method of working through this. Okay, are we okay with this process? All right, really, you're just doing the problem that you did from before, and then you just plug in the upper lower bound, right? Nothing really unexpected here. So what I do want to show you now, this is the preferred method that most of us prefer, that we want. It's easier. Let's just do everything in terms of U, bring in terms of back in terms of X, and then we can work in the bounds. Here's the other way of approaching, and I want to show you this method because sometimes AP exam problems present things in this form, and we should have to be able to be familiar with it. Okay. Now, if this is a pre-response question, you can always choose to do it this way if you like, but I do want to show you this other way. The other way is after you get to your antiderivative, okay, rather than converting it back in terms of X, the other option is conforming the bounds to be in terms of U, and then just do everything in terms of U. That's the other method. Okay, but that requires us to convert the bounds. So we're going to say since X is equal to 1, I do have a conversion between U and X, and that is my U substitution statement that I have there. This is going to be my conversion that allows me to get from the X variable to be in terms of the Y variable. So if I plug in 1, sorry, let me get this a little bit cleaner here. If X is equal to 1, and if we know that U is equal to X squared minus 2, then our adapted lower bound is going to be 1 minus 2, which is -1. Right? If my upper bound started off as X equals 2, then my U is going to be X squared minus 2, which is 4 minus 2, which is 2. So now I have my antiderivative. I'm going to leave it in terms of U. I have my adapted bounds also in terms of u. So I'll do u to the fourth over 4 between my new lower bound of -1 and my new upper bound of 2. I should get the same answer. (16/4 minus 1/4 is 15/4. Do we see the distinction between these two steps? I know students prefer this method, which is fine. There is some advantage with this method. The advantage is that you do all of your calculation on the front end. So when you get to evaluating your bounds, it feels a little bit cleaner because you've already done all the messy work. Everything in terms of u, so it makes a little bit less calculation. You kind of split up your calculation amongst these two. So, another thing I want to point out about this method is that if your lower bound, if you start with a lower bound of 1, whatever you get as your resulting value is still your lower bound. Even if it suddenly switches to be higher or lower than the other number, if it starts as lower bound, whatever you get is still your lower bound. If your number ends up being lower up here than down here, just still go through your process. You don't have to worry about making any adjustment. The math will work itself out, right? So if this is lower and this is higher, doesn't matter. I mean, you can flip the bounds, but then it feels like you're adding more work than you need to. Just go through the process, and there's no need to flip the bounds. You can still get the answer. Now, one thing that you do not want to do is this. I see some students do this. They would do integral of u to the fourth. Or sorry, they would find the antiderivative u to the fourth over 4, and they would do this. I know you're getting the same answer in this way, but what's wrong with this approach? There's a mismatch, right? Your antiderivative in terms of u, but then your bounds are in terms of x. There's a mismatch. I know in this case it works out, but I just want to point out that you either get everything in terms of x, or you get everything in terms of u, but you don't want to do a mismatch of u variable here and x variable there. Okay, so you guys have homework from 6.5. Come get your phones. Guys, I'm going to be pushing the test to Wednesday, and then the calculator portion is going to be pushed out to the next week or the week after. Probably not. Yeah, probably not. Right.
No way. Oh my God, it's gonna be an hour.